Hello, students. Today, we will study the evaluation of the implementation effects of sponge city construction. I am Deng Yaibing from Shanghai Urban Construction Vocational College. Let's review the content from last class. Last class, we mainly introduced the planning control goals for constructing low-impact development rainwater systems. This goal mainly includes several parts. The first is the total runoff control. The second is the peak runoff control. The third is the runoff pollution control. The fourth is the utilization of rainwater resources. The control indicators mainly include several. One is the annual total runoff control rate, the peak runoff control rate, the annual runoff pollution control rate, and rainwater utilization rate, as well as drainage and flood prevention standards. For implementation effect evaluations, we generally have the following regulations. First, an implementation effect evaluation should be conducted after sponge city construction. The evaluation work can be entrusted to a third-party agency to prepare the evaluation report, or self-prepare the evaluation report and organize expert reviews. Second, the evaluation of sponge city construction effects should include assessments of the annual total runoff control rate, annual runoff pollution control rate, rainwater utilization rate, and drainage and flood prevention standards. If conditions permit, an investment benefit analysis can be conducted in conjunction with construction and maintenance costs. The evaluation of sponge city construction effects should combine on-site monitoring, model algorithms, and indicator assessments. If conditions permit, on-site monitoring and model algorithms should be used. Otherwise, indicator assessments should be employed. First, let's look at the first basic content: the assessment of the annual total runoff control rate. What is the assessment of the annual total runoff control rate? It is the calculation of the rainwater amount controlled, not discharged outside the site, through natural and artificial enhanced infiltration, retention, storage, and collection and reuse after planning implementation, or project completion based on actual measured data and analytical calculations. The amount of rainwater controlled not discharged outside the site is calculated as a proportion of the total annual rainfall. So how do we assess the annual total runoff control rate? For areas with clear catchment areas, defined river outlets, and on-site monitoring conditions, it is advisable to conduct the assessment of the annual total runoff control rate through on-site monitoring. For individual facilities with favorable conditions, it is advisable to consider installing flow sensors at the outlets during design and construction. Through typical rainfall monitoring, the annual total runoff control rate can be calculated. For sites or projects with good research foundations and a wealth of data, for plots or projects with good research foundation and abundant data accumulation, model algorithms can be used to assess the annual total runoff control rate. The selection of relevant models and parameter values should conform to the characteristics of different sites and projects. Through steps such as data collection, model establishment, parameter calibration, and effect evaluation, the annual total runoff control rate can be calculated. For sites or projects with weaker research foundations and less accumulated data, indicator assessments can be used to evaluate the annual total runoff control rate. The annual total runoff control rate can be decomposed into regional systems, building and community systems, green space systems, road and square systems, and rainwater systems, and assessments can be conducted for each indicator separately. So, what indicators are there for evaluation? For example, in the Shanghai Sponge City Construction Indicator System, the indicator system clearly defines the indicators and objectives related to the annual total runoff control rate, which are targeted as follows: the proportion of green space in the area system compared to built-up land, the river surface ratio, the concentration of green space ratio in building and community systems, the green roof ratio, the permeable paving ratio, the water retention capacity per unit of hardened area, the green space ratio in the developed area of the green space system, the green space ratio in residential areas, the green space ratio in affordable housing, the green space ratio in public buildings, the green space ratio in key functional areas, the green space ratio in industrial parks, the ratio of depressed green spaces, the green roof ratio, the permeable paving ratio, the green space ratio in road and square systems, the permeable paving ratio of sidewalks, the permeable paving ratio of parking lots, the permeable paving ratio of squares, the ecological protection ratio of river and lake systems in the water management system. Evaluations will be conducted. This table presents the planning control indicators. For the main land types, assessment by adopting indicators. While assessing the annual total runoff control rate, we must also refer to the Ministry of Housing and Urban-Rural Development's technical guidelines for sponge city construction and related facility scale calculation methods to calculate and verify the annual total runoff control rate. When the indicator assessment and control rate verification both meet the standards, the annual total runoff control rate is considered compliant. The above is the evaluation using indicator assessment. Next, let us look at the evaluation of the annual total runoff control rate for monitoring projects. For monitoring projects, on-site inspections of various facilities should be conducted to ensure that infiltration, retention, storage, purification, and usage meet the design requirements for runoff volume control, and evaluate the effect of overflow discharge at the overflow discharge point or inspection well where the monitoring project connects to the municipal drainage network. Continuous automatic monitoring should be conducted for at least 1 year to obtain time flow sequence monitoring data. At the same time, at least 2 rainfall events should be selected with a deviation of no more than 10% from the project's design rainfall and with a rainfall interval greater than the actual drainage time designed for the facility from the previous rainfall. Designed for the facility from the previous rainfall. Municipal drainage network, there should be no discharge flow, or the discharge flow should be that after purification, treatment through infiltration, sedimentation, etc. This can determine that the project meets the design requirements. The evaluation of the annual total runoff control rate for drainage areas should meet the following provisions. Model simulation methods should be used for the evaluation. Simulate the calculation of the annual total runoff control rate for the drainage area. The model should have simulation functions for surface runoff, generation, pipe flow convergence, and source reduction facilities. Modeling should include parameters for source reduction facilities, pipeline topology and defects, surface conditions, terrain, and at least 10 years of continuous rainfall monitoring data with intervals of 1 minute, 5 minutes, or 1 hour. The calibration and validation of model parameters should select at least one typical drainage area Flow meters should be installed at the municipal drainage network's discharge points and upstream key nodes. Continuous automatic monitoring should be conducted in synchronization with the monitoring projects within the area to obtain at least 1 year of time flow or time water level. Sequence monitoring data from the municipal drainage networks. Discharge points or the front pond of the pump station. Select at least 2 rainfall events with maximum 1 hour rainfall amounts close to the design recurrence interval standards. For the rainwater drainage system, and conduct model parameter calibration and validation. Using the monitoring data from these events, the Nash efficiency coefficient for model parameter calibration and validation must not be less than 0.5. The annual total runoff control rate for the urban built-up area. The proposed evaluation area in each drainage area should be weighted by the area of each drainage area. This will yield the annual total runoff control rate for the urban built-up area proposed for evaluation. The previous section was the evaluation of the first key content. Next, let's look at the evaluation of the second key content. The evaluation of the second key content is the evaluation of the annual runoff pollution control rate. The annual runoff pollution control rate uses the overall annual reduction rate of runoff pollutants as the evaluation indicator, are often correlated with other pollutant indicators. The total reduction rate of annual runoff pollutants is measured by the annual total reduction rate of solid suspended solids. The annual reduction rate of suspended solids is equal to the annual runoff volume control rate in area multiplied by the average removal rate of suspended solids by sponge city facilities. This table shows the runoff pollutant control rates for individual facilities. Next, let's look at the evaluation method of the second key content. The annual reduction rate of solid suspended solids for individual facilities can be calculated by multiplying the annual runoff volume control rate by the facility's average reduction rate of solid suspended solids. The facility's average reduction rate of solid suspended solids should be obtained through on-site monitoring. The annual reduction rate of solid suspended solids for the region can be calculated by aggregating the annual reduction rates of solid suspended solids for different areas or plots through a weighted average based on the annual runoff volume for regions and plots with the necessary conditions. The annual reduction rate of solid suspended solids should be determined after monitoring and analysis based on local conditions. The evaluation of the third key content for assessing implementation effects is the evaluation of rainwater resource utilization rate. The evaluation of rainwater resource utilization rate refers to measuring the percentage of total rainwater utilization to total rainfall based on actual measurement data and analysis after project planning and implementation or completion. This includes the rainwater resource utilization rate for the regional system, building and community system, and the green space system. For example, Shanghai had proposed that sponge city construction should encourage the development of rainwater utilization rates. In regional planning control indicators, the rainwater resource utilization rate should not be lower than 5%. Resource utilization rate, which mainly includes the calculation of total rainwater used for road spraying, landscaping, irrigation, municipal miscellaneous uses, and industrial and agricultural production cooling. The amount of rainwater collected and used for road spraying should be calculated based on water measurement facilities If there are no measurement facilities, it can be estimated by calculating the capacity of spraying vehicles and the frequency of water withdrawal. For internal road spraying in enterprises, estimations can refer to local water use regulations. For internal road spraying in communities, estimations can refer to the water-saving design standards for residential buildings, the amount of rainwater collected and used for landscaping. Irrigation should be calculated based on water measurement facilities. If there are no measurement facilities, estimations can be made based on the water quota for landscaping irrigation. Internal landscaping irrigation in enterprises can be estimated based on local water quotas. The total amount of rainwater used for municipal miscellaneous purposes, industrial and agricultural production, and cooling should be calculated based on water measurement facilities. If there are no measurement facilities, estimations can be made based on local water quotas. The amount of rainwater used for replenishing landscape water bodies should be included in the total rainwater utilization. The water balance method can be used for calculations. The fourth evaluation of the implementation effect assessment is the evaluation of drainage and flood prevention standards. Drainage and flood prevention standards mainly refer to the design, recurrence periods of rainwater drainage pipeline systems and flood prevention facilities. The following two tables present the design recurrence periods for rainwater drainage systems and flood prevention measures. Next, let's look at the evaluation methods for drainage and flood prevention standards. The evaluation of drainage and flood prevention standards should include network assessments and comprehensive flood prevention level evaluations. The assessments of the network and comprehensive flood prevention level should be conducted according to existing regulations and standard calculation methods. In areas with favorable conditions, model algorithms should be used for calculations. The above describes the four basic components of the implementation effect assessment. Next, we will provide an example to illustrate the core indicator assessment of the construction effectiveness of the Sponge City pilot area in Kangshan. Kangshan City became one of the first Sponge City construction pilot cities in Jiangsu Province in 2016, and successfully entered the second batch of national systematic and comprehensive Sponge City construction demonstration cities in 2022, achieving a transition from pilot to demonstration. The area of Kangshan's provincial-level Sponge City construction pilot zone is 22.91 square kilometers. The terrain is flat with a dense network of internal rivers, allowing rainwater to flow into rivers by gravity, forming a drainage pattern based on the levee area. During the Sponge City pilot construction process, the drainage characteristics of the levee areas were fully integrated, collaborating on source, process, and end engineering systems, including river systems, levee area cycles, network improvements, flood-prone point remediation, and site and green space development. The river system and levee area cycle engineering include two aspects: the reinforcement of flood control embankments and the widening of river channels. 10 drainage gate stations were constructed in the levee area to enhance the flood control and drainage capacity. Dredging and cleaning were carried out on 8 rivers, while internal source remediation and the promotion of flowing water were conducted on 10 rivers. Ecological restoration projects were implemented on 9 rivers to improve the ecological environment of water bodies. The remediation projects for networks and flood-prone points include The separation of rainwater and sewage for 7 communities around 6 roads within the pilot area. The modification of 3 communities with mixed rainwater and sewage connections. And the construction of intersection projects for 3 old communities that do not yet meet the conditions for separation, achieving zero direct discharge of sewage. Upgrades were conducted on the networks of 2 flood-prone points in the area, the construction of a temporary drainage pump station and a low-lying community slated for demolition will be integrated into the overall plan during future demolition. A total of 103 sponge projects and green space engineering were implemented, including 28 for roads and squares, 46 for buildings and communities, and 29 for parks and green spaces. The overall technical approach for this assessment is to collect and organize basic data to understand the attributes and spatial data of sponge facilities, projects, drainage divisions, drainage networks, and river systems. Implement comprehensive monitoring including rainfall, river water quality, network water levels in the area, flow and quality of typical project outlets, effluent quality from typical facilities, and runoff quality from typical surfaces. Conduct monitoring analysis and model construction, including analyzing the runoff pollution characteristics of typical surfaces, the pollution reduction effects of typical facilities, and changes in river water quality. Develop a typical Project XB drainage assessment model and an InfoWorks ICM assessment model for the area and pilot zones, conducting step-by-step evaluations of facilities, projects, and pilot zones to quantify the core indicators of sponge city construction. This diagram presents the overall technical approach, which mainly includes 3 aspects. The first is the collection and organization of basic data. The second is the evaluation methods. The third is the assessment of core indicators for sponge cities. This is a photo of the on-site configuration of concentrated water samples for spraying and collecting blind tube water samples. This is a comparison chart of rainwater drainage flow monitoring and simulation processes at Huangmission Primary School. This is the distribution chart showing the relationship between the total runoff control rate and the solid suspended matter reduction rate of typical projects. Finally, let's look at the evaluation results. After 3 years of Sponge City pilot construction, the provincial level Sponge City pilot area in Kangshan has the flood prevention capability for a 1 in 50-year event. There are no black and odorous rivers in the pilot area, and the river water quality met the standards at a rate of 100% monthly in 2020. The total runoff control rate for typical years reached 80%. The pollution baseline for typical surfaces is clear. The removal rate of solid suspended matter in rainwater runoff for typical projects and facilities ranges between 50% and 65%.